All right, hello. In this series, in this video, we're going to be addressing a particular type of series, a series which is referred to as a telescoping series. And sort of the classic picture that you can think of in your mind is what if you had a telescope, like one of these sort of old-fashioned telescopes that sort of like collapsed in on itself. Well, then you could take the telescope and obviously extend it out to its full length, or you could collapse the telescope down to sort of just the first piece of it and the last piece of it. So you would still see the last piece, you'd still see the first piece, but sort of all the other pieces would sort of be collapsed in the middle. So telescoping series have this sort of structure. And, well, an example of this, to make this sort of more apparent mathematically, what about this series? This is a sum from n equals 1 to 25 of the terms 1 over n minus 1 over n plus 1. So each of these terms is, in fact, a pair of terms, but so be it. We could add up all of these terms. And if we would, what would we get? Well, the first term, which would correspond to n equals 1, would be 1 over 1 minus 1 over 2. Put a plus sign in between. We're doing sigma notation. This is the way we deal with series in this notation. Now we're up to n equals 2. n equals 2 would be a half minus a third. I'll write out n equals 3 just to get us a handle on the trend. What would this be? 1/3 minus a fourth. And if we go all the way out, we could get out to n equals 25, because, well, that's all the farther we're going to go, because the sigma notation tells us to stop there. We'd have 1 over 25 minus 1 over 26. Now, I claim that this sum is a whole hell of a lot like that telescope above, in the sense that a bunch of the terms cancel, in fact, leaving only the first and last. Because note, if you added up all of these terms, you eventually subtract a half and add a half. But what happens if you subtract a number and add it? Well, of course, those things cancel. Minus a third plus a third, minus a fourth plus a fourth. And in fact, prior to this 1/25th, you'd have a minus 1/25th in the previous parenthesis. So that 1/25th would cancel. And check it out. What are you left with? You're left with the first term, and you're left with the last term. So here's an example of a telescoping series. You get a bunch of terms, but whenever you ultimately add it up, you collapse down to essentially just the first and the last. And the definition of a telescoping series could be this: a series for which the sum of the first n numbers cancels to be all but the first k terms and the last k terms for some fixed k. Now, in the example above, the k was 1. There was only one term in the beginning or the end, but as we'll see as we get into these telescoping series, sometimes you have a telescoping series where you might have 2 terms left in the front and 2 terms left in the back. So be it. But a telescoping series will always cancel to leave a first k terms in the beginning and a last k terms in the end, and that's it. Now, also remember, when you add up the first n numbers in a series, this is an especially important measure, or especially important value, when it comes to determining the value of an infinite series. Because if you want to add up infinitely many numbers, how do you do it? Well, you add up the first n of those numbers, and then you take the value of that and compute the limit as n goes to infinity. So here you're not computing the sum of the first 1,000 or million numbers. No, you're computing the sum of the first all the numbers out to infinity, in effect. Right, and where could that come into play? Well, how about in this example here? So now this example is essentially an infinite series to correspond to the finite series, which is above. And it's essentially an extension, a generalization of the problem that we sort of worked above. Now, we want to find the sum of these infinitely many numbers. How do you find the sum of infinitely many numbers? Well, you compute what the sum of the first n of them are, and then you take the limit as n goes to infinity. So, first piece, figure out what the first n of them add to. So we're going to have to do that with this sum as well. So we're going to compute the sum from n equals 1 to capital N of 1 over n minus 1 over n plus 1. And in fact, this is going to look a whole hell of a lot like what we did above. In fact, that's why we did what we did above. So the first term is going to be 1 over 1 minus 1 half. And then we get 1 half minus 1/3. We know how this trend goes. Here, though, we're not adding up to 25. We're adding up to capital N, so that we're getting the sum, or the formula for the sum of the first capital N numbers. So instead of getting 25 here for our ending number, no, we're going to end at capital N. So we'll get 1 over n minus 1 over n plus 1. And now, using the same observation that we used previously, that this is a telescoping series, we can cancel a bunch of terms. In particular, the minus a half and the half, the minus 1/3 will cancel with the third in the next. And just like that 1 over 25 had a corresponding minus 1 over 25 in the previous parenthesis, so too this 1 over n would have a previous minus 1 over n in the previous parenthesis. And what we can see then is what results for the sum of the first capital N numbers is 1 minus 1 over n plus 1. That's it. That's what the sum of the first capital N numbers are. So if you added up the first 100 numbers, you'd get 1 minus 1 over 101. Add up the first 1,000 numbers, 1 minus 1 over 1,001. Now, we don't want to know, though, what the first 1,000 numbers add up to. We want to know what the first infinitely many numbers add up to. We're looking for the sum of this infinite series. How do we do that? We take the limit of the sum of the first capital N numbers. So to evaluate this limit, what do? We take the limit as n goes to infinity of 1 minus 1 over n plus 1. Note, that fraction that includes n is a bottom-heavy fraction, so as n goes to infinity, that fraction is going to go to 0, and ultimately this limit evaluates to 1. So what does that mean? Well, since the value for Sn as n goes to infinity was 1, that means the sum of our infinitely many numbers is 1. So, state the result. This series converges to 1. If you took these numbers and added them all up, what would you get? You would get 1. And when I say all these numbers, that's actually infinitely many numbers, which is pretty damn cool because, well, I mean, how many times in your life have you added up infinitely many numbers? Well, depending on how much, I guess, work you've been doing leading up to this week, a decent amount. But hey, this is probably a pretty fresh idea, and I think a pretty cool one. Okay, so one more example to get ourselves a solid grip of these telescoping series. What about this series? So this is a sum from n equals 1 to infinity of 3 to the n plus 1 minus 3 to the n plus 3. So first thing we'll do to try to get a grip of what's going on is we're going to try to get a value for the sum of the first n numbers in the sequence, or rather the first n terms. So we'll start at n equals 1, and I get 3 squared minus 3 to the 4th. The next term is going to be for n equals 2. I get 3 cubed minus 3 to the 5th. Next, we would get n equals 3. That would be 3 to the 4th minus 3 to the 6th. Now, if you noticed, actually, when we even only had 2 of our parentheses written out for our sum, notice none of the terms canceled at that point. And at this point, it's the first time that we actually got cancellation. The minus 3 to the 4th canceled with the positive 3 to the 4th. Right, so this is the sum of our first n numbers. We could take this all the way out until we got to capital N. At that point, we'd have 3 to the n plus 1 minus 3 to the n plus 3. Okay, sweet. So we need to add up all of these terms, and well, the fact that this is showing up among the telescoping series is sort of suggestive of the fact that we might have a series that functions like the telescope and cancels to the first how many terms and the last many terms. But now think about this. We saw cancellation with the minus 3/4 and the 3 to the 4th. Right, so now where would we next cancel? Well, think about this. The next parenthesis that would appear would include a 3 to the 5th minus 3 to the 7th. Notice the 3 to the 5th that's added there cancels with the minus 3 to the 5th. What would the next parenthesis include? The next parenthesis after the parenthesis that started with 3 to the 5th would start with 3 to the 6th. It would be 3 to the 6th minus 3 to the 8th. Well, that would cancel with this 3 to the 6th. And what you can see is there's exactly 2 numbers that are appearing at the end, or excuse me, at the beginning. And subsequently, in fact, if we go to the end, it would be the same result. So this 3 to the n plus 1 would cancel with a minus 3 to the n plus 1 that was previous. However, in the parenthesis that is immediately previous, we would get 3 to the n minus 3 to the n plus 2. And notice, this 3 to the n plus 2 has no subsequent term of 3 to the n plus 2 to cancel with, just like this minus 3 to the n plus 3 has no subsequent term of 3 to the n plus 3 to cancel with. Whereas this 3 to the n cancels with the minus 3 to the n that came previously, this minus 3 to the n plus 2 has nothing to cancel with. And as a result, we'll have, just like the two numbers that appeared in the front of our series that didn't cancel, we'll have two numbers in the back of our series that don't cancel. So when we add up the first n numbers, we get 3 squared plus 3 cubed minus 3 to the n plus 2 minus 3 to the n plus 3. Right, so now what do we need to do? To compute whether or not this series converges, we need to evaluate the limit of that expression. So now we take the limit as n goes to infinity of Sn. And what we can see here, whenever we take the limit, oh my goodness, we've got 3 times itself a bunch of times. The fact that 3 is bigger than 1 in absolute value means that each of those terms would tend to infinity, and our limit here diverges. So as a result, what can we say? We can say, therefore, this series diverges. So if we add up the terms of this series, when we add up all infinitely many of them, we're going to get some value that's either not well defined or is plus or minus infinity. And if I may, just to take one final minute to sort of summarize what we've seen with infinite series so far, I claim we've seen essentially 3 circumstances where we can determine, when we have infinitely many numbers, whether or not the series will converge. And I should add in a bit here. What if we had a series that contained infinitely many values? So what if we're adding up these infinitely many numbers? What if, let's say, the terms of the series do not limit to 0? Well, if the terms of the series do not limit to 0, then as we saw, it doesn't matter what non-zero number you add to itself infinitely many times, you always get an infinite result. And then we can say definitively that in this case, we diverge by the divergence test. So should your terms limit to a number other than 0, well, then that means that you would diverge by the divergence test. We also saw series that were geometric series. Those were series of the form a constant times an exponential term in particular that starts at r to the 0 or 1. Well, we saw that these converge precisely when absolute value of r is less than 1, and in particular we saw what they converge to, so we can actually determine the value of these sums precisely. We notice that these sums also diverge otherwise, so when your multiplier is 1 or bigger than 1 in value, you would diverge here in the geometric series case. And what we saw in this little video today was to describe telescoping series, and these were series that sort of collapse down to just the first k terms and the last k terms whenever you're computing the sum of the first capital N terms. So when you're computing the nth partial sum, you'll get the first k terms and the last k terms, and everything else cancels. Well, how can you compute the value of such series? Well, just like you can always, you can compute the value of the partial sum and then just let the n corresponding go to infinity. So instead of counting up the first 100 numbers or 1,000 numbers, count the first infinitely many numbers. And if you do that, in this case, well, you'll get whatever pops out. Sometimes you diverge, sometimes you converge, but nonetheless, this is the technique for computing the value of a telescoping series. Find the value of the nth partial sum, and then take its limit.